everyone, and in today's lecture we're going to be talking about Astar. Astar is a search algorithm that we'll define later, but essentially the idea is we've talked about graph search. We were able to use BFS to get the lowest number of action path through our graph, but what if we started weighting our edges based on some cost? So if our edges have some associated cost for traversal, we need to slightly change the breadth-first search algorithm in order to find the cost optimal path. So we can do this as a cost-based search problem. So before we had a search problem that was trying to find the sequence of actions that transforms the initial state to the goal state, full stop. We weren't really cared about this definition of optimality. But now that we're doing this cost-based search problem, we want to find the sequence of actions that transforms the initial state to the goal state with the minimal cost. So now we're back to our general graph search problem, but you can see the numbers along these edges now represent how costly it is to traverse those edges. So can we find the path with the least amount of cost? And the answer is yes. So we can use our generic search algorithm again. So this is our generic search algorithm, and we can do the exact same things that we did before, but now we're going to pick the successors based on the cost. So let's say I have some node that's connected to some other nodes through some edges. What I did in breadth-first search was I looked at this because all of these were essentially the same. They were weighted 1. I'm looking at the next depth. But now what I can do is say that I want to search this state first. But now what I can do is I can sort my open list based on cost. So I expand the node with the lowest cost first. So let's see an example of what that looks like. So this is going to be a naive cost search. So we're going to be using essentially breadth-first search, but now it's based on the cost. So the way we pull something out of the open list is based on what's the lowest cost. So we have our open list and our closed list again. So what I'm going to do is I'm going to have some node, and then I'm going to do a dot and represent the cost. So S has a cost of 0 because we're starting there. We don't need to do anything to get there. So I expand S, and I have S0. Now that I've expanded S, I can add A, which comes from S, and it has a cost of 1 because this edge has a cost of 1. So the cost of getting from S to A is 1. I also have B, which comes from S, and that cost is 2. So next I will expand A, and that will give me C, which comes from A, and it has a cost of 4 because I sum up the entire path. So I have to go from S to A and then A to C. So now it's 4. So then I expand B, so then I expand B, B from S, which is a cost of 2. And what I will get is I have some E, which comes from B, and it has a cost of 3. And I have some D, which comes from B, which has a cost of 7. So next I will expand E. So E comes from B with a cost of 3. And from E I can see F, which comes from E with a cost of 4. So I'm going to break the tie just arbitrarily and pick this node first. So I have C, which comes from A, which is a cost of 4. And that's going to give me G, which comes from C with a cost of 24. Now I'm not going to end the search here because I want to see if there is a path with a lower value. The next thing I can expand is F. So I have F, which comes from E, has a cost of 4. And that will give me D, which comes from F, which has a cost of 1, 2, 3, 4, 5. Now we kind of have a problem here. So I can get to D from B with a cost of 7, and D from F with a cost of 5. If we don't correctly recognize that this is going to the same node from a different predecessor and correct our open list, you could potentially find yourself in a place where you get a cost that is higher than you need to, and you have a shortcut to the node. We would have a problem, and we'd only know how to connect these two. So what we need to do is remap this based on this shortcut. So that changes our algorithm a little bit. So the change in the algorithm will look something like this. So now everything looks essentially the same, except now we're going to look a little bit more specifically at each successor. So at each successor, we're going to say if it is not in the open or the closed list, just do what we were doing before. So compute our cost and insert it into Z in the open, sorted based on our cost. But if it is an open and it can be reached by a shorter path, What I want to do is update that node so that it has the new parent with the lowest cost. So what that would look like here is that I would remove this entry and essentially replace it with this. I have the lowest cost trajectory to get there. If I were to do that, I would then expand D to F, and I would get D from F, which is equal to 1, and this would give me G from D, which is equal to 6. And this would be our path. So the lowest cost trajectory is to go from G, whose parent is D, D, whose parent is F, F, whose parent is E, and E's parent is B, whose parent is S. So this is the lowest cost trajectory with a cost of 1, 2, 3, 4, 5, 6. Now, any other path that we can figure out, you have this one, which is a cost of 7, or you can have this path with a cost of 24, or you can have any path that goes through F and goes to G, and this will be much larger than 6. So this algorithm allows us to find the lowest cost path. And with the reconnection, this is generally called uniform cost search. So you're going to pick your successors based on what has the lowest cost next, and if you see something that you've seen before, but you can get there with a lower cost, use that route. So uniform cost search is optimal and it is complete. If you ignore zero cost, there's some weird cycling that can happen if you have zero cost cycles, but we're just going to ignore that for right now and say that you will get the optimal path. You will find a solution if one exists. But just like we had with the breadth first search problem, uniform cost search searches nodes in this way, just based on cost. So it looks just like breadth first search. So you can actually essentially think of uniform cost search as if I have a node here connected to another node, the cost of 3. All I need to do is add 3 additional nodes into here and run breadth first search. So this expands a lot of nodes, right? And if we have a really large problem, you're going to have to look at every single part of our state space. If we have a large state space, this causes a problem. So is there a way that we can use some information to get to a solution faster? And the answer is yes, and that's kind of the idea behind Astar. Before we talk about it, we're going to talk about heuristics. So a heuristic is a fast to calculate function that gives us an estimate of the cost to go. So let's say I'm trying to get from point A to point B. A heuristic could be something like, well, there might be an obstacle here and here and here, but it would essentially be the function that goes, what is the straight line distance between these 2 points? So it's something I can compute really quickly. It doesn't require a search, and it gives me some idea of what direction to go. There's no reason for me to go this way because I'm not making progress towards my goal unless I've already searched everything here. Now there's a couple of properties that must be true about heuristics for them to work in Astar. So the heuristics must be admissible, which means it must be an underestimate of the true cost. That means I can't overestimate it. I can't have a heuristic that tells me it's farther to go than it actually is. We must always under-approximate. For every node and every successor, the second property is consistency, which is a stronger property, and usually it's very hard to get an inconsistent heuristic if it's admissible. So what this says is that for every node n and all of its successors n prime of n generated by any action, so I have my node n, and then I have some action which gives me some n. The estimated cost of reaching the goal, so this is our heuristic function h, from n is no greater than the step cost, so this is the cost of n to n prime, plus the estimated cost of n prime, which is our heuristic of n prime. So everyone usually struggles on consistency. So let's look at what that equation looks like mathematically. So all it's saying is that the cost to go from some state n to some other state n hat, that heuristic at n has to be less than the cost to go between the two plus the heuristic at the next state. This is a generalization of the triangle inequality. And the important thing is to remember that it's very hard to get an admissible but not consistent heuristic. You can do it, but a lot of things that you use, like the straight line distance, will be both consistent and admissible. You usually don't have to worry about this too much. So now we have Astar, and what Astar is going to do is just like uniform cost search, except this g function is the true cost to get to that node plus some heuristic which we approximate. So here I have the heuristic in green, and the cost to traverse some edge in purple. And let's see if we can get to the optimal trajectory in fewer nodes expanded using A*. So let's look at our heuristic values and see if the heuristic that we have is admissible. So all that means is that it has to be an under approximation of the actual cost. So we know that to get to F to G, the lowest cost trajectory is this trajectory of 2 here. So our heuristic of 1 is admissible. We have this E, which our heuristic is 2. So we know that the cost to get there is actually 3, so it's admissible for that position as well. D, the cost to get from D to G is 1. The heuristic is 1. It only has to be less than or equal to, not strictly less than, so this is admissible as well. And it's actually admissible for all of these different nodes. So now that we have that, let's try to do the A* problem. So we have our open list and we have our closed list. So we're going to start with S, cost of 0 plus a heuristic of 0. We're going to expand that, so S is equal to 0 plus 0. And that from that, we're going to get A, which comes from S, with a cost of 1 plus a heuristic of 20. So we have our open and our closed list, and our open list is going to be sorted based on the summation of our heuristic and our cost. So we're going to start off with S, and that's going to have a 0 cost plus a 0 heuristic. It doesn't really matter what the heuristic at S is because there's not really any other options anyway. So we're going to expand this, S of 0 plus 0. And that's going to give us B, which has a cost of 2 plus a heuristic of 4. And then A, which is a cost of 1 plus a heuristic of 20. Now this is the key thing that's different from uniform cost search. So if we go back up to uniform cost search, what you'll see is that I actually needed to expand A first. Because it has the lowest cost, I have to expand all those points. But based on my heuristic value, I know that's not a good way to go. So I can use that information to not expand that point later on with A*. So now we can expand B. So we have B, which comes from S, which has a cost of 2 plus 4. And from B, we have E, which comes from B and has a cost of 3 plus 2. Now it's really important to always sum the true cost of the path plus the heuristic at the current node, and do not use any prior heuristics. You have to keep those separate. And we have D, which comes from B, the cost of 7 plus 1. So we can see that 5 is lower than 8, so we can expand this next. We have E, which comes from B, 3 plus 2. We get F, which comes from E, which is a cost of 1, 2, 3, 4, plus our heuristic of 1. So then we would expand F, and from F we get D, which comes from F, which has a value of 1, 2, 3, 4, 5, plus 1. So we remove this node as well. And then we have G, which comes from F, which then has a cost of 1, 2, 3, 4, plus 14 plus 0, because the heuristic at G must always be 0. And then we expand D to F, and then I'll expand D to G, and we get out the optimal path that we had before. But we still have this A here. We never searched this side of the graph because using a heuristic, we were able to know that that was not a good way to search. It did not make sense to go in that direction. So A* is only optimal if we have a consistent heuristic. Remember that consistency is a stronger property than admissibility. So if we have a consistent heuristic, we must also have an admissible heuristic. If we change the heuristic so we could possibly be forced to search in the wrong direction, we would potentially not expand the nodes that will give us the lowest cost trajectory. So it is only optimal if we have this consistent heuristic. Then A* will also find the path in the fewest number of expansions given the information it has. So if you compare it to any other graph search algorithm, you will tend to get the lowest number of expansions, but this depends a lot on the heuristic you're using. The better your heuristic, the fewer number of expansions you need. If you theoretically had the heuristic that gave you the true cost to go, you would just search the optimal trajectory essentially. And A* is also complete. It will always find a solution. So these are really nice properties. Essentially, we can guarantee optimality if we know something about our heuristic, It will expand a few number of states, unlike other problems, which will expand a lot, and you can focus this search direction pretty strongly. And it's complete. We will always find a solution if there is one. These are kind of the best of all worlds when it comes to search algorithms. So in summary, Astar is a great search algorithm that gives an optimal path, but it can be slow depending on your state or action space. You still have to expand all of these nodes, and if you don't have a good heuristic, you'll end up spending a lot of nodes. And if you do that, that could potentially take a long time to do. So there are other solutions that might be better depending on your state and action space. Like we talked about, LQR would be really great for that. Doing what we did with LQR with Astar would be very, very difficult. But doing things like planning over a long horizon with LQR would be completely impossible. So these are kind of the trade-offs that you have to consider when you're doing search. How you can break down your problem so that you can do a search and then control to track that trajectory is the traditional way that we approach this problem. Well, that's all for this course. I hope you all learned something, and we'll continue to move along in RoboJackets. I still poke my head into meetings every once in a while, so feel free to poke me on Slack or grab me if you see me on campus. I really hope this course was useful.